There's been a slight change of schedule, and we've added a 50-minute open discussion after the 3 talks. The idea is to have the questions during this discussion session, and as a result, the lunch will start at 12:30 p.m. instead of 12:15 p.m. as stated in the schedule. And our first talk is by Leonhardt from St Andrews, and he's going to be talking about perfect imaging with positive refraction. Ulf.
Yeah, thank you very much for the invitation to this wonderful conference. And thank you for coming to listen to perfect imaging with positive refraction. The work I'm going to report on was performed by several people, most notably Yungo Ma from Zhejiang University in China, and also from several institutions. And I'm now joined another institution as well as a part-time professor at not very far away from here, at Guangzhou in China, South China Normal University. The question I'm starting with is essentially for this field how to go beyond invisibility. What comes next? I mean, what are the next interesting subjects where we can apply the lessons learned from transformation optics in the real world? And one approach clearly is to go into different subjects. I mean, to go away from optics to acoustics and other areas where wave physics matters. But in optics, what could be the next step? And my argument is that it's essentially going back to the starting point of this field. And the starting point was this paper by John Pendry from 2000, where he showed that a slab of negative refractive index material is able to make a perfect lens. The subject of that is perfect imaging and super resolution. Now, this subject has been at the heart of modern optics. And modern optics started with the work of these 3 gentlemen, whose pictures you see on the slides. And one was the professor of natural philosophy at the University of Jena, Ernst Abbe. And he had the great fortune of working together with the university technician, Carl Zeiss. And they also had a third person, Otto Schott. He was a glass chemist and entrepreneur. And these 3 people, in their work together, they created the entire modern optics industry. It all started in Jena around 1870s. And one of the starting points for this was the understanding of Ernst Abbe of what limits the resolution of optical instruments. He understood that it is the wave nature of light. And in particular, he found an expression for it where he showed that in principle, you cannot focus, you cannot observe small structures smaller than about half the wavelength of light because of the wave nature of light. Now, this effect is, or this limitation to traditional optics is very important these days. And one of the examples is that it's at the heart of modern technology in photolithography. So what you see is a cartoon of a photolithographic process. You photograph structures onto the surface of a chip, and for this you need a lens system, and it's just a cartoon of what happens in reality, what you see there. But in any case, so it is then the resolution limit of those lenses that limits the structures that you can make in photolithography. So if you want to have a higher level of integration, then one of the limitations comes from the wavelength of the light you're using. So the industry moved away from working with visible light to ultraviolet light, but there are also there are still limitations and arising difficulties. So therefore, it would be a great advantage if there is a trick around the standard diffraction limit of imaging. And that's why that paper has become so important, and showing that negative index materials may provide an answer to this problem. We showed in 2006 that negative refraction is also an example of transformation optics. And what it does, it performs a transformation of space that amounts to a folding of space. And why that is a way of, why that can perform perfect imaging is nicely illustrated with these pictures from a review article by one of the organizers of this conference. And you see there, if you have a folding of space, then in virtual space, real space is folded. So a single point in virtual space amounts to 3 points in the folded regions of physical space. And electromagnetism in virtual space is the electromagnetism of empty space. And therefore, at 3 points in physical space, you have exactly the same electromagnetic field. And then you may argue that amounts to a transfer of the electromagnetic field from one place to another with a resolution that is not limited by the wavelength of light anymore. And therefore, you may get perfect imaging. Now, that picture wasn't known when negative index materials or their analysis started. And when that started, there was a huge discussion about the reality of negative refraction in around 2000 to 2003. And that discussion, I think, was largely settled, and it was settled by experimental demonstrations, that indeed you can have super resolution with materials that are similar to negative index materials. And one of these experiments was performed by Nick Fang, who's going to give a talk at this conference later on. Now, the disadvantage of those setups is that what you can actually make in practice are only so-called poor man's perfect lenses. So these are thin slices, much thinner than the wavelength of light, because then you don't need to have a material with both negative epsilon, negative mu. Negative epsilon is enough, and you can have that with ordinary metals. And another problem is this, that if you want to extend this over large distances, then the losses in the material become an important issue, as has been mentioned by John Pendry already, and they limit the resolution of these devices. So therefore, it might be a good idea to look for alternatives to this. And one is a positive alternative to negative refraction, and that actually is very old. And in order to find this, all you have to do is to open Principles of Optics by Born and Wolf, and there's an entire section called Perfect Imaging. And the subject goes further back. It goes back to works by Maxwell himself that he did as a student at Trinity College in Cambridge, and it was given a beautiful geometrical form by Luneburg around 1944. The idea of this is related to transformation optics. So you have a transformation from virtual space to physical space, but the difference to what is normally called now transformation optics is this, that the virtual space is curved. So it is the surface of the sphere, the simplest curved space, that is then transformed onto a plane in space, for example, and so you imitate with a dielectric material the propagation of light on the surface of a sphere. Now, that has some unusual aspects. One is that if you look at light emitted from a point on the surface of the sphere, all the light rays coming from this point will focus on the antipodal point again. And that translated into physical space means that all the light rays emerging from any point in space will meet at another point. And it also happens that on the sphere, the light would propagate in circles, and the projection from the sphere to the plane, called the stereographic projection, preserves that quantity, so light also goes in circles. So with these devices called, in this case, a Maxwell's fisheye, it has two properties. Light rays are circles, and light rays emitted from any point emerge at a corresponding imaging point. And you can simplify that and make it more practical by putting a mirror around the equator of this virtual sphere and confining light to one of the hemispheres. And in this way, you have the same effect as before with the entire sphere. You just create the illusion that light propagates also in one of the other hemispheres, and but you still get the focusing. And in physical space, it amounts to what you see on the right side, so that light emitted from any point inside of your device will focus at a focal point on the other side. This is similar to the behavior in an elliptical mirror. The difference is that in an elliptical mirror, you get that effect only from one focal point to the other focal point. In these systems, in Maxwell's fisheye mirror, you have that for any point inside. Now, but we learned from the work of Ernst Abbe that it is not ray optics that limits the resolution of imaging, it is wave optics. So what about waves there? And now, intuitively, you may understand that if the picture behind this is simply wave propagation on a sphere, then if you imagine light is emitted at one point on a sphere, then a wave would go around the sphere and would perfectly focus on the other side as well. and therefore it would be natural to assume that the perfect imaging behavior is also maintained for waves. And I did the calculation for that, and you can see from these pictures that it is indeed true. You can then project the behavior of the sphere down to the plane, and you get a needle-sharp image when you have a needle-sharp force. That property is preserved if you surround the material by a mirror in order to confine the refractive index into a finite range, and then you get the same focusing from one point to another point with perfect accuracy. So that idea published in 2009, and little did I know that it also became a very controversial subject, so there were lots of comments on this paper, and even comments on replies on comments of this paper. And if you want to read more about this, there's a News and Views focus in Nature about perfect imaging with positive refraction. And so clearly that subject needs to be settled. And it can be settled by experiments. And we did 2 of those experiments. I would like to report on the 2. And these are demonstration experiments. And their purpose is not to perform actually perfect imaging for visible light, but to demonstrate the physical mechanisms behind that. And they are done with microwaves, because microwaves are such nice electromagnetic waves to work with, because you can measure the fields exactly, and you can understand with great precision what is going on in these experiments. Now, the microwave devices we use, they look very similar to the cloaking device you have seen already. So they're made of circuit boards, layers of circuit board, and with the structures in those layers, we can imitate a refractive index distribution and achieve the required refractive index distribution for Maxwell's fisheye surrounded by a mirror. And another ingredient we need are sources and detectors. The sources and detectors, they are simply cables inserted between or in one of the metal plates that you use to confine the microwaves, as you have seen in the previous talk for the microwave cloaking experiments. And so we can use one cable as a source, and then we have another cable as a detector, and we also have a cable to scan the field in the setup. And in this way, we have indeed demonstrated that perfect imaging is possible, or that imaging with subwavelength resolution is possible. And it's important now to make some distinction between these type of experiments and the standard way how the diffraction limit arises in standard lenses. And let's have a look at this view graph. So this is the standard behavior, or this is a normal lens. And where does the diffraction limit come from? Well, you can start from describing wave propagation in free space using the Helmholtz equation. And then what you can do is you perform a Fourier transformation in a plane. This is because lenses in this setup, they are planar devices. So the object is you have your object confined into a plane. Then light propagates, it hits a planar lens, and then it's focused on the image plane as well. So propagation goes from one plane to another plane to another plane. And therefore, in the mathematical analysis, what you do is you perform a Fourier transformation in this plane. If you do that, you see that you can solve for the propagation in a very easy way. So your Fourier transformed field at another position z along the axis of propagation is simply given by the original Fourier transform field times an exponential factor. That exponential factor contains in its exponent a quantity that depends on the square root of the wave number squared minus the Fourier component squared. Clearly, if those Fourier components are larger than the wave number of the light you're working with, what you get is a purely imaginary square root, and therefore you get an exponential decay. This means that given a propagation over several wavelengths, then those components would decay. These are the components that contain the information about very fine details of your image. And they correspond to what is known as evanescent waves. So they are decaying waves. They are no longer there in the Fourier spectrum. And then if the lens, what the lens does, it simply performs a Fourier transformation of the far field into the image. If those Fourier components are missing, clearly you don't get a perfect spot anymore. Now, compare this with those perfect imaging devices. They are not planar. So all the light rays, or all the light fields, I should say, emitted from a point is captured in all directions. And that's the main difference. And then you cannot apply this analysis anymore, because if you talk about evanescent waves in particular, then those are waves that are confined to surfaces. So because we are talking about an exponential decay in one direction, that implies that there must be an exponential growth in the other direction. And that makes only physical sense if you have a preferred direction of propagation. That is no longer true in these systems. And therefore, the evanescent waves are not the relevant issue in the analysis. The near field is not the evanescent field. Now, another issue with those experiments is that you get only the perfect imaging if you, or the perfect resolution, if you actually look at it, if you detect it. And we did this simply in the simplest possible way, that we have one cable that serves as a source, and then we have no detector cable, and we just scan the field. And what you see is that you get a focus on the other side, but that focus is limited by the diffraction. And the field behavior agrees very well with an analytical theory that you can formulate. Now, that is related to an issue that Richard Feynman raised on the diffraction limit. He didn't believe in the diffraction limit. He objected to this. And Feynman's objection to the diffraction limit is based on the simple fact that Maxwell's equations are time reversible. So if you have the emission from one point, then what you can do, you can simply time, or you can inverse the electromagnetic fields, and then you can focus on the same point again, or another point if you want to, and with the same precision. So, but the important point is, if you want to time reverse the entire emission process, you also have to time inverse the source of it. Now, there's a beautiful illustration of this in acoustics, so done by Matthias Fink's group in Paris, and where an acoustical source is emitting a sound wave, and that sound wave is then time reversed. You can easily do that in acoustics, and then it goes back to the original spot, and there the inverse of the source was applied, and then you see that the acoustical waves can really very, very narrowly focus. Now, the difference of this, so this illustrates that in order to get the subwavelength resolution, you can do time reversal, but you also need to reverse the source in order to see that. Now, in our case, we don't have an active source. What we have is just a detector, a cable, waiting for the wave to arrive. In particular, what we did is we had, in the last experiment, we had two sources, and then an array of 10 detectors, 10 cables waiting for the electromagnetic field to arrive. And then what we did is we were seeing how much of the electromagnetic wave is arriving at which detectors, or how is the electromagnetic wave concentrated at those detectors. And this shows that you don't need to impose a current on the other side, on the detectors, in order to capture it. You can do this passively. And also the time reversal is done passively, because Maxwell's fisheye amounts naturally to a time reversal of electromagnetic waves. And considering the behavior of the sphere, so the wave propagates, and as they expand on one side, they must converge on the other side. So this is both, in its way of propagation, in its way of detection, a completely passive way of achieving a time reversal in imaging. And if you look at the pictures that we've seen in the experiment, they really show a subwavelength resolution. And in that particular experiment, we achieved a resolution that was better than lambda over 5. Now, how do you want to get further in the optical range? So we did some preliminary steps using silicon photonics, where you can make Maxwell's fisheye lens as a silicon structure on a silica substrate. We didn't do this for a Maxwell fisheye lens. So far, we did demonstrate this for a Luneburg lens, but the technique to make these devices is also suitable for creating Maxwell's fisheye lenses there as well. They're a related experiment, and so this work is also partly inspired by a paper by Shalayev's group, where you can achieve this with micro droplets. So you just have a droplet on a surface that curves, and it can also act as a lens and approximate the behavior of the required lenses for perfect imaging. So this is one experiment. I would like to report on a second one where we showed that you can achieve subwavelength resolution with materials of, in principle, arbitrary low index contrast. In the Maxwell fisheye lens, the index contrast is a factor of 2, but it's possible to go down and to have, in principle, an arbitrary low contrast. This goes back to a problem discussed by Luneburg. And the problem is this. So if you want to achieve a situation as shown in the picture, so a light ray goes from one radius to another radius with a specified angles, then you can solve that problem. So you can find out what refractive index distribution you need in order to make a well-defined scattering of light by radial symmetric substance. Now, for imaging, what you need is closed trajectories of light rays. And in this picture, it amounts to simply setting the radius R1, the inner, the radius, as the same as the outer radius R2. If you do this, then you can compute the refractive index profile that you need, and it's shown in the picture you see there. And you see that the smaller you make the inner radius where your substance sits, the less index contrast you need. The price you pay for this is that you have a gap between the outer mirror surrounding everything and the substance inside. And that is shown in these pictures. So what you see on the left side is a situation when you put a source in this gap, so only some of the light rays, only those light rays that hit the substance show the right behavior, so they form closed trajectories. But also light rays that are scattering around, they would not form closed trajectories, but rather irregular ones. And on the other hand, if you place the source inside, then indeed you get this perfect imaging behavior, at least on the level of light rays, and therefore this is a candidate for a perfect imaging device as well. Now, I would like to argue that this behavior is actually sufficient to get perfect imaging, also for light waves, not just for rays, although the design of these devices is governed by ray optics. And the argument is this. I mean, first you have to remind you that geometrical optics is a wave theory. It is not ray tracing. The rays are simply the guiding lines of waves. What happens here is that those guiding lines tells you how the wave emitted from one emitter is then concentrated on the other region on the imaging side. Geometrical optics cannot explain the near-field behavior, so what happens around the source. But then you can say, well, if you zoom in, and it's shown in this picture, that this is the behavior of light propagation on a very short scale. So there you can essentially assume your material is homogeneous. And for homogeneous materials, as long as you fit the boundary conditions, it will focus or on one spot, or on the other side, it will describe the emission of the source. So the key point is that you use geometrical optics in the far field, and as long as you match the far field correctly, then you can focus the waves in the near field, and there you don't need to talk about geometrical optics, but you use then the exact expression you can get for an homogeneous material, and you match the two together, and in this way you can describe perfect imaging even using geometrical optics as a guiding principle. And that we illustrated with our experiment. So this is, I show you the setup again. And what we did there was similar to the previous case. So we had two sources. They are in two cables as source points, and then an array of detectors. Now, what we did is two things. So we recorded the field concentration at the detecting cables, and we also measured the throughput through those detectors. And we realized that we did not see the concentration by just looking at the field concentration. So there, as you see from the diagrams, you don't get you don't get peaks at the spots where you would expect them. You get some interference pattern instead. So, but you see this in the throughput. So you see that in the field that is actually measured by the detectors. There you see that you can discriminate between the two sources. And in the experimental demonstrations, these pictures. What you see there are two graphs. So one is black, the other one is gray. The gray refers to the situation where, if I go back, the source is in the gap between the material and the mirror, and where you would not expect to have perfect imaging. And the black curves correspond to the situation on the right-hand side, where you have the sources inside. And indeed, if you look at picture C, then you see for the black curve, you get a double dip, and so a gap between the two spots that is consistent with the position of the two sources, whereas for the gray plot, you don't see that. So that really demonstrates that first, if you meet the right conditions, you can indeed achieve subwavelength imaging with such low index materials. But the experiment also demonstrates that it's much more sensitive than the original Maxwell fisheye. I mean, after all, we're using a very crude approach to this. We approximate a continuous material by a discrete metamaterial structure by using these circuit board materials. And so we are certainly not perfect with the material we're using. And this is not so important for the original Maxwell fisheye, but it becomes critical if you squeeze the system to its limits. So if you try to reduce the index contrast, and the price you pay for this is that you have a gap between the mirror and your material, and you have to design everything very, very carefully. Of course, then you could argue if the index contrast is really very low, then you can work, instead of metamaterials, you can work with dielectrics, and there you naturally have continuous behavior, or you can work with waveguides, tapered waveguide that have or that imitate a refractive index distribution and achieve this effect in a continuous fashion as well. So there will be room for this, and where you can indeed get subwavelength resolution with materials that can be made in practice. And where would be their applications? I mean, you could imagine you place such a lens on top of a chip and then transfer the light field from one place to another with a resolution that is not limited by the wavelength anymore. And maybe that has some applications in lithography as well. But the real application for the time being is that this is simply, it's a myth buster. So it tells you that a few things you take for granted in nanophotonics are not right, and they have to be modified. It tells you that, and what are these myths? So amplification of evanescent waves is needed for super resolution. That is not true, because there are systems where evanescent waves are not the issue. The near field is not the evanescent field. Don't confuse that. And near field information is lost in propagation. That is also not true. The near field information is perfectly there using Feynman's argument, because Maxwell's equations are time reversible. So if you have a source, then if you could time reverse the field, then even the near field is still there. And it can appear if you then offer your field the potential of creating a drain in a time reverse source. Detectors do not change images. In this case, it's an interesting aspect that you only get the image if you see it, and you get it in your detector. As in particular, the last experiment showed where we only saw the enhancement when we are in the field recorded by the detectors. And geometrical optics can indeed predict perfect imaging. Thank you very much.
So the experiment you have done does not show that very far away from your sources, you can obtain resolution. What is the wavelength in that case?
Just look at this picture. So it's about 3 times. So the device is about 3 times the wavelength.
Right.
So it's not on the order of lambda.
Well, I would call this borderline, experimentally. Okay. So, but let me, I mean, if I have things like this, whether I will be able to see them 1 lambda apart, or 2 lambda, or 3 lambda apart, is a matter of how good my experimental setup is. It's a question of signal to noise. Now, if you could repeat that experiment 100 lambda apart, and see, I bet a nickel that it's not going to happen.
What are you going to bet? I take the bet. So
And the other thing, I can't speak for Feynman, but I remember reading about this business.
Sure.
He didn't quite say what you think he said. He was talking about something significantly broader, and the question of whether you could convert a source into a drain. So we can talk. I mean, it's impossible to say all this in a couple of minutes.
Lectures, and you can also read more about this in an article by Gerd Loix on the focusing of light with mirrors in optics communication.
So let's have a bet.
I think
can we finish with a bet?
Very quickly.
Sure.
So I bet that if you repeat that experiment with a device that is 100 times lambda, you are not going to see anything.
Okay.
Okay, that's the bet. There's time for one.
But you haven't said what your bet is, so how much you're betting it.
Let's talk about it later.
Yeah, later. Ross.
Is spatial symmetry an important part of your achievement of super resolution? In other words, it strikes me, for example, this last one you had to have R1 equals R2. And it's obvious if you have a field which is spatially even, then its resolution around the source point is going to be the same as its resolution around the image point.
Well, the fields are not even. So as you see, they're oscillating and they're inhomogeneous, the fields themselves. But in one respect, I mean, for the systems we know, they're all radially symmetric. And this is because of the Luneburg's inverse problem. So, but I also know that they exist in the mathematics literature. There's a much more extended work on this. And so presumably you can also do this with devices that are not homogeneous. And
okay, thank you very much, Alf. Let's give another round of applause.
I wanted to thank CT and John for organizing a wonderful conference in a wonderful location. So I'm going to talk about discrete transformation, elastodynamics, and active exterior cloaking. And I'll say in a minute more about that. First of all, I wanted to point out that transformations are easy to work out. Of course, transformations of equations date back a long while ago, in particular connections with general relativity. But it's rather straightforward to derive the transformation optics and transformation elastodynamics. And here I've taken following the work of Colin and Vogelius, who relied on variational principles, but applied just to the conductivity equation, just as a simple example. And you start off with your equation. You multiply it with a test function, W. If this is true, if we multiply it by a test function and integrate it over a region omega, the equation still holds true. And then if our test function W vanishes at the boundary of the region, you can integrate by parts and get this equation here. And then it's just a simple change of variable in the integration to come to this equation at the bottom. Here, A is the Jacobian of the transformation, and that just enters through the chain rule. And of course, when you change variable, you also change the volume, which is why you get the factor of determinant. And then you integrate by parts again, and you arrived at the new conductivity equation with the transformed conductivity variable. And the same argument holds true for Maxwell's equations as well. So it's rather elementary to derive the transformation rules, and you don't need to go through general relativity. I'll just mention a application of this that as to composite materials is that if you've got a periodic composite material and you transform your coordinates by this equation here by a linear term plus a periodic term, then actually there's an associated transformation of the local conductivity given by this and the effective conductivity given by a similar formula, which implies that if you know the effective conductivity for one structure, you can get the effective conductivity for a whole variety of structures as well. And of course, that's not just true for effective conductivity, but also effective dielectric constant and effective magnetic permeability. So John has already given a very nice introduction to transformation-based cloaking, which dates back for conductivity to Greenleaf, Lusses, and Ullmann. Ulf had a different approach that he applied to two-dimensional geometric optics, and Pendry and Schurig and Smith derived it for the full Maxwell's equations in the time harmonic case. And then that was followed by the experimental realizations, and in particular, the calcite-based cloaking is a very nice example where the transformation is piecewise constant that John already talked about as well. And then for acoustics, basically the same arguments apply, and that was shown by Kumar and Schurig, Greenleaf et al., Chen and Chan, and Kumar et al. And what's interesting is you require a fluid with anisotropic density, an appropriate bulk modulus, or as Norris showed, a pentamode material cloak. And so the idea of anisotropic densities goes back to work of Schoenberg and Sen in 1983, finding that a laminate of two fluids could essentially have an anisotropic density. And actually, you can get this simplified model here, where here we've got masses in cavities and springs with different spring constants in the horizontal and vertical directions. And then when you oscillate this back and forth in this direction, it's got a completely different inertial response to if you oscillate it back and forth in this directions. And the surrounding matrix could be rigid, which shows that it's not an effect of the elastic constants, it's actually the effect of the effective density. And then the springs could have some damping. In that case, the effective density will be complex. And in fact, the density can also be negative, as shown by Chang et al. In 2003. And these are some experimental realizations of pentamode materials by the group of Martin Wegner in this year. And so this provides an alternative to the use of anisotropic mass, and the pentamode. So this pentamode here is a little bit like water. It's got a very low shear modulus and relatively high bulk modulus, and but generally pentamodes, by adjusting the structure, you can get materials which support any combination of bulk and shear, but are completely compliant with respect to all orthogonal loadings. And so pentamodes, that's in 3 dimensions. There was constructions of what's group of Norris called metal water. Basically, you take a metal structure and you've got it air in between and surrounded by some membrane on the outside, and it basically has the same properties as water. And then there's results of Farad et al. For cloaking for water waves, and acoustic cloaking of the group of Zhang, Xia, and Fang. And so they're here, for example, you've got, in the absence of a cloak, you've got a distinct shadow zone. When the cloak is present, you get relatively little shadow. So I mentioned or showed at the beginning how the equations of conductivity transform. The equations of elastodynamics, how do they transform? Well, basically, it's the same idea. You start off with your equations, and you find out that they transform under this transformation here. So here we let the displacement field transform in a different way by some function b of x, which is a matrix-valued function. And you find out that the equations of elastodynamics transform to these equations here. And so the interesting thing is that elastodynamic equations, in contrast to the equations of electrodynamics and acoustics, don't keep their form under coordinate transformation, but you need new coupling terms. Alternatively, the elasticity tensor C doesn't keep its symmetries. To begin with, when we looked at this transformation, we're interested in transformations where the elasticity kept its symmetries, but it's also interesting to have a look at transformations where it actually loses its symmetries. And that's the case if you don't choose B equals A. And so that most general transformation was first obtained by Narish and Shaleyev in 2011. And if the case B equals A, it reduces to what we found before. And then, interestingly, when B is equal to identity, in other words, when you don't transform the displacement field, but just leave its components invariant, then the coupling terms actually disappear, and the transformed density tensor remains isotropic. And this was the case analyzed by Bruggenau and Milton in the two-dimensional cloaking example. Also, I should mention that for Maxwell's equations, that corresponds exactly to continuum elastodynamics, but just having a elasticity tensor C, which is anti-symmetric in the first and second pair of indices. And so in that case, if C is anti-symmetric, then it's easy to work out these coupling terms actually disappear, and so you'll retain the forms of Maxwell's equations. And so actually to go through that transformation, it's quite straightforward. You see how the gradient of U transforms, and then you start with your elasticity equations, multiply it by a test function, do an integration by parts, and then you arrive at the transformed equation. So exactly the same as in the conductivity example. Chan and Hu noticed that if the transformation has got slow variations, then it may be good to neglect the second order derivatives. In that case, the coupling terms disappear, and you get a new effective density, which is anisotropic, and new elasticity tensor given by this formula here, that they applied to a direction for beam tenor in the work of Chang et al. And if S and D are not zero, that actually corresponds to equations that John Willis derived, and are the elastic equivalent of the bianisotropic equations of electromagnetism. And so those additional coupling terms do have some interpretation, actually. So the coupling terms mean that the stress is not only related to the strain, but it depends upon the velocity, and the momentum doesn't just depend upon the velocity, but also depends upon the stress. So there's coupling terms just like in bianisotropic equations of electromagnetism. So I wanted to talk about discrete transformation elastodynamics. And so the idea is that if you've got some network, so here the straight lines are springs. The circles are terminals where you apply forces, and the black dots could denote masses, for example, or internal nodes. And suppose you've got some network of springs and masses, and now suppose we do some transformation to a new network where we've just changed the coordinates of each point. And then obviously when we do this, we've got to decide how the forces and displacements also transform. And the simplest thing to do is to let the displacements here equal the displacements there, and the forces at any node here equal the forces at any node there. And then obviously one has balance of forces and at each node, and including the inertial force, that is. But when you do that, if you've got a force acting in this direction on this node, if we're just translating the forces, you end up with a force acting in this direction on that node there. And so to do that, we actually require to replace this spring here by a new sort of spring where you've got a force here, and then on opposite, you'd have an opposing force here if this was a normal spring. And so if you just translate that spring there, you've got an opposing force in this direction. And so what you need is a new type of spring, which we call a torque spring, where the forces are equal and opposite, but not aligned with the line joining the terminals. And so this is an example of a realization of a torque spring. So again, the straight lines are just springs. And here we've got a mass and another mass there. And these junctions here don't actually have any mass. They're just their point junctions. So this is a mathematical idealization of a torque spring. In practice, you'd actually like to, this is completely floppy, you'd like to add some small springs and things like this to give it a little bit of rigidity. But this structure here, when you can shift these base points, translate these, and you don't excite the masses at all, but if you push here and at the same time pull there, then that excites the masses, and so the net result is that the forces at the nodes here are equal and opposite, but not aligned with the line joining them. And so here's another example of one of these torque springs. Again, the forces here are masses, and these are springs, and this shows the direction of the forces when the masses are activated. And again, the force is not aligned with the line joining these torque springs. And so the idea is to, when you do the transformation, this discrete transformation, you should replace each of these springs by one of these torque springs. Or if you've got a periodic material or apply it to a continuous material, you can think of the material as being replaced by some discrete network, say a triangular network. Then you'd apply that transformation to the triangular network, and then you'd replace each spring by one of these torque springs. Of course, when you do that, these are sort of rather bulky, and you're going to end up with intersections between springs. And but what's interesting is that crossing springs do not actually interact within the framework of linear elasticity. So if you've got two metal wires and they cross, there's a short circuit at that crossing point. That's not true for springs, actually. And in particular, so here, the black lines you can think of as two crossing springs. If you pull this end of this spring to this point here, what happens is that the point of intersection moves to this point here, but the length of this spring here is, within the framework of linear elasticity, the same as the original length of this spring here, so it remains relatively unstretched. And so crossing springs don't interact, actually. And so you can actually superimpose these sorts of structures, and so basically a network of springs can behave macroscopically as an elastic material, and you can basically apply the rules of discrete transformation elastodynamics to get the desired response. So I just wanted to finish with talking about broadband active exterior cloaking, and this was sort of modeled by work that I did with Ross McFedrin and Nikolai Nukarijic and Lindsay Bodden on cloaking of caused by superlenses. And here we've got a set of polarizable dipoles near the superlens, and the dashed region is the cloaking region. And what's sort of interesting in this example is the cloaking region is exterior to the cloaking object. So this is the cloaking region, and it's outside the cloaking object. And then there was work of et al. Used based on the principle of complementary media that showed you could get cloaking exterior to the cloaking device as well. And so you might ask, well, can you do this more generally? Instead of using materials, can you use active sources? And here this is the solution for quasi-statics. And so basically we've got an antenna at one point here which produces this field, and it cloaks this black object here. And so this turns out to be mathematically equivalent to the problem of finding a function which is an analytic function or a polynomial which is 0 in one disk and 1 in another disk, which you think would be contradictory, but you can actually cook up such polynomials that holds an arbitrary degree of approximation. And this shows the result for Helmholtz equations. And so here we've got a object which is scattered, but here we've got three devices which produce fields that create a quiet zone and allow the wave to propagate through. The fields in this region are incredibly intense, and so from a practical viewpoint, you'd want to replace this by a boundary with antennas around the boundary. What's interesting in this results is the existence of these throats here, and you know by, let's see, you know by Green's theorem that you can create a cloak, and this was the cloak of Miller. You can replace a cloak by putting sources around a boundary. If you try that same so this shows that you can create a wave which would cancel the incident wave within this region here by putting sources all around the boundary. If you actually try creating gaps, even small gaps, by removing those sources, you don't get anything like a cloaked field at all. And so what you can instead do is replace the sources on this region of the boundary using the addition theorem by a source at this point here, replace the sources at this point by a point there, and so forth. And using that, you end up with these three sources here with a throat which sort of connects the, this will turn out to be the cloaked region when you add in the incident field, and with the outside region. And the same works in 3 dimensions as well. And so this is for 3-dimensional acoustics. You've got 4 sources that you need. And you create a small red region here, which is the cloaked region, which cloaks you against incident fields. However, using this approach, you need to know the incident field in advance or have the incident field slowly varying. And then you can also apply the same techniques, and this was done by Chang et al. In 2010, to active illusion optics, where you can have the scattering from an apple given by this field here. If you replace it by the appropriate devices around the outside, you can actually mimic the scattering of a banana. So anyway, at that point, I'll stop. Thank you.
Yes? I didn't quite follow where you had 2 springs crossing
Yes.
And then you said that they didn't interact. Could we see that slide?
Yes,
again,
sure.
please?
This is just the physical representation. You can show it mathematically. Whoop. Wait a second. Maybe it's easier to go. Yeah.
Yeah, that's it.
That one, yes.
Yeah. Now, the point I didn't understand was, I take your point that the spring on the dotted line only increases in length by second order.
Yes, that's right.
But the force perpendicular to it is first order, and that changes.
You mean the force in this direction?
Yes.
Yeah, yes, yeah.
Is your theorem still true despite the diagram?
The theorem is still true despite the diagram, okay. Actually. So we've got, yes, I mean, it's a good point, actually, that the angle there is different, but I guess in reality what happens is that when you actually increase this here by first order, then the deflection of this line from there is of higher order. And so this diagram is a little bit inaccurate. But,
okay.
Yeah.
Ross?
Graeme, you mentioned in passing pre-stress.
Yes.
Pre-stress is something you can do in pre-stress is something you can do in elasticity, but less readily in electromagnetism. So can you briefly expand on your comment on pre-stress materials and what they were doing in that case that you mentioned in passing?
Yeah, so that was work of Norris, that if you have a pre-stressed material and you superimpose a small stress upon it, the elasticity tensor loses its symmetry. And so I'm not familiar with an electromagnetic analog of that, but yeah.
Sebastian?
I guess it would be chirality, no? By anisotropy again. I think what you meant is that pre-stress is equivalent to Coursera type. Somehow you just break the minor symmetries.
That's right.
And
yes.
if you break the minor symmetries in the elastic context, it's most likely that you end up with a bianisotropic material in the electromagnetic context. No?
Yeah, I think it's a little different. Well, the way I think about the electromagnetic, the elastic bianisotropy is a little bit like the Willis equations, and so that's a little bit different to breaking the symmetry of the elasticity tensor.
One more question? If not, let's thank Graeme again for his talk.
I'm Jensen. I come from the City University of Hong Kong. So this is one of the local universities in Hong Kong. And if you want to come to visit us, so come to talk to me, I will take you a tour to City University of Hong Kong. So the topic I want to discuss today is about acoustic and electromagnetic double negativity by coiling up space. So what I want to show you today is a special scheme, an alternative way to make acoustic matter materials. So the scheme is called space coiling. And if we use such a special scheme, we can mimic some of the one-dimensional elements that can have a high refractive index. And then if we can put these high index elements together, assembling them into 2 dimensions, we can bring down the band gap to very low frequencies, and then we can have a geometric route to double negativity, large index, or a density near 0. So at the same time, I will also show you some experimental results that recently we have done on them, so that to demonstrate double negative acoustic matter materials using this scheme. And then we will show that the same principle can also apply to EM waves. So here, because a large part of this talk is related to acoustics, So that's why I put one slide to have a very brief summary on different ways to achieve extreme acoustic properties. So on the left of this slide is the I call it metamaterial route. So this is the complete analogy to the EM wave metamaterials. In this case, instead of epsilon and mu, in acoustic we have to do physics on the two constituent parameters called the density and the power modulus. In this case, we just an analog to the EM waves, we need resonating structural units so to generate our phase response. And then we can create resonance in, for example, in density in this case, or in the power modulus in this case. So in this case, if we have a vibrating mode in resonance for the last sphere oscillating in a rubber cushion, then we can get a negative density. In this case, if we can have a resonator, a breathing mode in resonance inside a Helmholtz resonator, in this case, we can generate a negative power modulus. So these are by the resonances. In these cases, by talking about density and modulus, we are already having a valid effective medium description in them. And if we put these two kinds of resonances together, then we can generate a double negativity. So in this case, instead of epsilon mu, we have the density and power modulus being simultaneously negative. But people sometimes may not want to use the resonating structural units because maybe we want a lower loss, maybe we want a larger bandwidth, or we want an easier way to scale it up to 3 dimensions. So people are seeking different ways to do the same job. So very interestingly, there is another route by using phononic crystal, which I show on the right-hand side. So in this case, this is an alternative route to metamaterials. They are working in different principles. So for example, in this case, we are working beyond the effective medium regime, going into the intermediate frequency regime. So we rely on the Bragg diffraction, we rely on the band folding or equivalently. In this case, therefore, we don't have a rigorous effective medium in this case. But very interestingly, there are many phenomena we found in metamaterials. Also, we can observe by using phononic crystals. For example, we have the perfect lens or the super lens in metamaterials. By using phononic crystal, we can do subwavelength imaging as well to focus a subwavelength spot from one side to the other side. So in this case, we can also have negative refraction by using a phononic crystal. So they are very similar to each other in some sense. So actually, the idea, we can trace it back to a very early paper. In this case, we can use a photonic crystal to demonstrate, to mimic super lens with negative index. Or there are many recent examples also. So for example, in this case, we can use photonic crystal to construct a photonic crystal in a higher order by alternating stacking positive and negative indices together to demonstrate a 0th order Bragg gap. Also, there are some very recent examples that in this case, we can use photonic crystal to design the dispersion surface, so to mimic an invisibility cloak, which is usually found only in metamaterials. In this case, we can have using a photonic crystal to mimic a direct point and then also the 0 index. So to me, it is not so different for the two cases, like phononic crystals and metamaterials. We think that if we can bring the band gap even down to a lower frequency, then they are really similar. Then they become really similar. If we can do that, then we can have a very effective medium. So in this sense, in acoustics, what I'm mentioning here, we can have both well-defined density and power modulus. Even above the band gap, we can then achieve extreme material parameters without the usage of the resonating units. So here are two cartoons to show you what is motivation. So the left-hand side is the usual one, that the effective medium before the band folding is only valid in this regime. If we can have really high index as the constituting materials, then we can bring down the gap to a lower frequency. So the effective medium will become valid for several bands. Then we can generate extreme effective parameters and extreme acoustic properties. But this is not usually easy for in many cases, because in nature we don't have materials with very high indexes. So for example, this will be very difficult for airborne sound, which is we are interested in this case, that normally the sound speed in a material is travel much faster than the one in air. So equivalently, we have index less than 1 in this case. There are some exceptions. For example, silicon rubber can have a sound speed much lower than the one in air. and equivalently has a high index, but they are usually very lossy. So in our scheme, we actually try to mimic it, this high index, by using metamaterials, by using microstructures. So the scheme is showing here. So we rely on a special property called cutoff-free guiding. So in this case, this is just a normal conventional waveguide, the wave propagate along here. If we have cutoff-free wave guiding, then we can curl the curve just like this, and then we can delay the propagation. So equivalently, just concentrate on these elements, then it will equivalent to have a very high index. So in this case, we can mimic a one-dimensional element with high index. So and then if we can assemble them, okay, into two-dimensional ways like this, the one-dimensional high-index element. If we assemble them into a way just like that, then we can have a metamaterial, and the band gap can be brought down to much lower frequencies. So before I go on, I just want to show you the two of the fabricated metamaterials that we try to demonstrate this phenomenon. So this one is for acoustic wave. So these are the channels. We curl the wave propagate along these channels. So this is one of the unit cell. This is the simulation. And if we shine the pressure beam from the left-hand side of plane wave, then you see that the wave propagate actually along these curved channels. So from this point to the center of this unit cell, this is one element of this one-dimensional high-index element. We put 4 of them together, then we can generate this metamaterial. Actually, we rely on what we call the cutoff-free wave guiding. This is not the only case. We can work for two-dimensional acoustics, three-dimensional acoustics in this case. We can also equally apply it on EM wave as well. So if we convert this pattern, this curl pattern, onto fabricate using onto a couple wires, and then fabricate, stack them into layers on the PCB box, and then we can have equivalently metamaterials for EM wave. But we'll come back to this very soon. But for easier understanding, let me first concentrate on the acoustic case. So this is the band structure. I plot, this is the unit cell what I'm mentioning. And this is the band structure. I'm plotting it using the normalized frequency unit here. And this is the Broughton zone. The reason is that you can see that when I plot in normalized frequency, you can see that the band folding occurs at very low frequency now. So 0.2 here means the wavelength is already 5 times of the netted size in this case. So in this case, the effective medium should work. So to further confirm this, we can also plot the dispersion surfaces, the contours of this band structure at different bands here. And they all look circular around the gamma point, the first band, third, and the fifth band. So by putting these together, low frequency and then circular dispersion, then we have effective medium becoming valid. So in this case, we can use S-parameter retrieval, okay, standard procedure in extracting effective medium. And the results are not sensitive to different directions. And I show you the particular case that along the gamma X direction. So these are the results. We can extract the effective index N, and then the impedance Z here. And then, for example, in the first band, in a really low frequency, then we observe that there is a high index regime. So in this case, just confirm that the one-dimensional elements are having high index. And then if after the band folding regime, so in this case, we still have very low frequency here, but we can see that actually the index now becomes negative. So in this region, very small frequency we still have. And then it corresponds to a double negativity in the density and Bow modulus. So I emphasize that this is still valid for the effective medium. So now we can use this rho and B to do further things. So we further go on to do some experiments to verify this negative index behavior. And these are the results. So here, what I show you here is the experiments that I try to use the S-parameter retrieval method experimentally. So we measure the T and R complex coefficients, and then we extract using the S-parameter retrieval. The dashed line is the simulation results. The circles are the experimental results. You see that I'm plotting index, real part of density, and real part of the reciprocal of the Bow modulus. So they correspond to epsilon and mu if this is EM wave metamaterials. And you see that they agree to each other really well. So to confirm that, for example, at around 2.7 kilohertz for this sample, we get a negative index of -1. And also experimentally, we can also extract the imaginary part of the refractive index, which I show you on the lower right panel. the dashed line is theoretical result, that the solid line is one of the experiments. We can see that actually it still has some absorption. And in this case, at 2.7 kilohertz, we can achieve a figure of merit around 5, which means the real part, the magnitude of the refractive index over the imaginary part is around 5 for this case. This is actually limited by the loss. The loss is actually limited by the viscosity of the air for the acoustic traveling around the channels. So we don't have this in EM wave, but in acoustics, it has to be limited by the viscosity here. And if we can further scale up the structure, this loss will further go down. So this is the result of the effective medium. So if we have such an effective medium, we can represent the metamaterial and use the metamaterial to build up larger structure. So in this case, the simplest structure, if we go up, is a prism, for example. So here I show you some simulations in this slide. So in this case, we are simulating a prism in different situations. This one is 45 degrees for the angle. This one is 18 degrees for the inclination angle. And then on the left, we show you the simulation with all the microstructures. On the right, with the effective medium, so for the two cases. And we concentrate at a frequency around n equals to -1 in this case. So you can see negative refraction here. And more importantly, they all agree to each other very well for the effective medium and the microstructure. For the beam direction, they are very comparable. And also, they agree to each other for the amplitude, also even the phase. So and in different situations, so the effective medium we extracted is a very good definition for the metamaterial and well representing it. So here I show you one frequency. So experimentally, we can scan through different frequencies. So this is a schematic. So just one point here is that this green line is the boundary between the negative refraction or negative index and the positive refraction corresponding to positive index. So we measure this green line also correspond to graph of this green line here, theory and experiment. The y-axis is the frequency, the x-axis is the angular information we measure from the exit beam. So you see that actually the experimental results also agree very well with the theory one, and show that the reflection angle can vary from negative value to positive value in this range, corresponding to index -1 to 1 in this frequency range. So this is the angle. So this is one example. So if we have prism, we can also do other kind of structure. So in this case, we can further confirm the negative index by using a slab geometry. So this is one slab. We put many units together. So this is one slab of this double negative space coiling metamaterial. So in this case, we do the simulation and experiment again. We fix the incident angle to be 30 degrees here. And then the green line are also differentiate the negative and positive index in this case. Also the green line, the vertical one here. Frequency is the y-axis, and the position is the shift of the beam at the exit side. So on the left, it shows the negative index. On the right, it shows the positive index. And you see that actually they are, again, they agree to each other to showing that the negative index appears in this regime, shows up negative refraction. The positive index here shows up as positive refraction. And they agree fairly well with the Snell's law from the theoretical results shown in the purple line also. So if we pick the two frequency at n equals to 1, at n equals to -1 at this view graph, and then plot it here for the beam profile, you see the dots or circles are the experimental result, and the solid line are the theory result, and to show you they agree to each other. So there is also a regime that we are not covering here. So this regime corresponding to the total internal refraction. When the index becomes too small for the magnitude, then we have total internal refraction, and actually the shift will be governed by the tunneling instead. So this regime is the additional regime. So what I have shown you already is the acoustic case. So because the principle, we can still confine the wave within the waveguide. EM wave for 2 dimensions is still true, can still be valid. So here we demonstrate the electromagnetic case. So this is the unit cell, and these are the couple wires of the pattern, and then we stack them in the vertical direction. So in the vertical direction, this pattern, these wires form a vertical wall actually. So these wires actually form effectively a conducting wall for the EM wave. So we can confine the H polarization wave within this channel again. So the physics are very similar. The only difference is that the band gap around the gamma point will be a little bit larger than before because there is additional impedance in this case when we stack them into layers instead of a continuous wall. So in this case, I show you again the view index, epsilon and mu here. In this regime, we have the negative index corresponding to double negativity. The loss here, actually, in principle, it can be very low, but in experiments, okay, because in microwave it's a perfect metal, nearly. So, but in experiments, because we are doing the experiment by using two horns in the open space with the sample in between. So in this case, we have additional scattering loss. So that's the reason why we have some loss here. And we obtain a figure of Merville around 10 in this case. Okay, so this is the final result. I want to show you that we also repeat the case for the EM wave with the slab now, and then we measure the beam shift. Again, we can show that we have a negative refraction around this frequency regime predicted by Snell's law, and also this we have positive refraction for a positive index. So this is all the results I want to show you today. And so in summary, okay, I have shown you an alternative route in achieving matter materials, so that we are achieving that by a very special scheme called the space coiling. And we can achieve double negativity by experiments for both the acoustic and EM waves. And we believe that the effective medium description here will be useful for further applications. For example, what I haven't shown you is that about a very special phenomenon about density near zero tunneling or the transformation acoustics. So this is what I want to show you today. So this is the group members. Without them, it can never work. And this I want to thank the funding agencies as well. So thank you very much.
Thank you, Jensen. Questions now. I think if we start with some questions on Jensen's talk and then move on to the general questions. Yes, Ulf.
So I didn't quite catch it. So how large are those structures? So the coils you're using, So I didn't quite understand how large are the coils you're using in comparison with the wavelength. My impression was it was about the same order, isn't it? And
no, it's much smaller than that.
I see.
It's a subwavelength because the reason we can have a subwavelength structure is that we coil it up, so the wavefronts travel along is elongated for many times, for a couple of times. So the band gap happens at a very small frequency. So this subwavelength should be about 1/5 of the wavelength because you can see from
you're still talking about band gaps. So the question is, how is this related to phononic crystals?
So from my perspective, they are now very similar in this case because
the point is there are two wavelengths. There's a wavelength in the vacuum and there's a wavelength in your structure, yes?
That's right.
And your structure is smaller than the wavelength in the vacuum, but not smaller than the wavelength in your structure. Is that correct?
No, of course, the effective medium, I'm working around a gamma point, so depends on how near to the gamma point. So this is a wavelength in the medium.
Yes, but your lattice constant must be 1/2 wavelength in the medium, yeah?
No, for example, in this case, lambda is already 5 times of the structure. Wavelength, I mean is the wavelength in the free space.
Yes,
in the free space.
Thank you. Is that okay? Yeah. Ross.
Jensen, a couple of times you actually showed a diagram of wave propagation both in the acoustic case and the electromagnetic case. And you said there was a purple line which was from Snell's law.
Yes.
And the simulation, you said they agreed, and it didn't seem to me there was any correspondence whatsoever. So perhaps you could go through that a little bit more slowly.
Okay. So this is the case for the acoustic wave. So maybe we can use this case to. So this is the purple line. So these are the Snell's law. So we see some fluctuations on the amplitudes. The reason is that we still have impedance in the system. So because of the impedance, you see the fluctuation. But more or less, you see that in this regime, the Snell's law predict a negative refraction, and in experiment, we also observe the same. So, or in this case, here we have a positive refraction, positive index, and the Snell's law also predict. So we are plotting using the view, the actual amplitudes.
Okay, so actually in the slab? What's the purple line say in the slab?
In the slab. So okay. So this is the position. This is the frequency. So this is not the slab. This is not the slab. So this is the frequency. This is the position. Position is this one. So we scan through here. We scan through outside the slab. We also scan through the frequency. So Snell's law predict what should happen if we neglect, for example, impedance. And then this the purple knife. This is what we show here. And then so, for example, let's say this frequency at 2.7 kHz, we have index roughly -1, and then we see we should predict a negative position. So if we measure, scan it through, so we should predict the beam should concentrate here. So this is the experimental results we show here. So this is like this. And if you want to particularly a frequency like this 2.7 kHz, we show this. This is the theory prediction. It's shift to the left, so it means that negative refraction. So this is the theory curve. So we put all the microstructure into simulation, also effective medium. They agree to each other. So this is the prediction in the solid line. And then we do the experiment. So these are the square circles. They overlap with each other.
With a point on nomenclature, I think probably Eli would call your coiled space a meander line, wouldn't you, Eli? Is that what an electrical engineer would call that structure?
Yes, or capacitor. It's just geometry.
Yeah.
So
Okay.
yeah, this is a purely geometric way to achieve this double negative index.
I think Roberto was...
Yeah, very briefly, I think you made a convincing argument that you can use effective parameters to describe what you have in a certain region. But I have two questions about this. If I look at this as X-ray scattering, in some sense, that's what it is for the people working in optics. In addition to your main beams, you have other beams in there that you do not have in situations where you can describe a medium in terms of an effective epsilon and mu, correct?
So yes, so what you're talking about, I guess, is the higher diffraction orders. Right?
And you must have those here, right?
So but they are evanescent in nature.
Oh, in this case?
In this case, yes. So if we are confined working in low enough frequency, so in this case, it's already a few times of the lattice constant, and we are concentrating around the regime that is around the gamma point, then we don't have this
All right.
problem.
And very briefly, the other question I wanted to ask you, why don't you get anti-crossing in there? Why, or you do?
Can you repeat once more?
Why don't you open a little gap in there?
Oh, okay. So it's a more complicated issue. Okay. So we have, along the gamma m direction, the gap is really small. This is contributed by the impedance mismatch when they join together at the center of the unit cell. Around the gamma point, you can imagine the phase just travel and then without any interference at all. But along the gamma x direction, okay, so if we go back to here, this is the gamma x direction. Suppose the waves travel in this case, and then we see an impedance mismatch branching out. So this will open a band gap here. So around the gamma x direction, we see a huge band gap. So this is how it comes from. Okay.
One more question.
Yeah, so for the EM wave material, so it's easy for me to understand the origin of negative epsilon coming from this holding wire. So, but what the origin of negative mu? Is it the coupling between the two layers?
So this is different to the resonating structure. So we are not seeing it as a resonating electric dipole or resonating magnetic dipole. So here, instead of the currents traveling on the wires, so let me show. Instead of these currents along the wires giving you resonance, this is not the case here. Instead, we have the waves traveling in between. So if you are looking at the H field, so actually you see that it's propagating within the channels. So they are not confined on the metal. They are not driving the current to get the resonance.
Like a waveguide.
It's more like a waveguide, yes, exactly.
Well, any more questions for Jensen before I open up the discussion? Okay, let's give Jensen a round of applause.
Thank you.
Are there any further questions people would like to ask or points of discussion they'd like to raise?
So John, we have a bet here that is $1 for each lambda over n. For
Right. Okay. Who's going to keep the kitty? Eli.
So maybe I can help the discussion get going. So that was an interesting bet and an interesting paper we heard. And it suggested that it was possible to focus electromagnetic energy to a very small spot and way below what would normally be the diffraction limit. And it's very hard to argue with Feynman, right? You can have a little tiny source, an atom. We have little oscillations inside the atom, and it'll send out some outgoing waves. And there's no doubt that time reversal will send those waves right back onto the atom. So I think you lose the bet immediately. If you believe Feynman, you've already lost. Don't even bring it up.
You guys have misrepresented Feynman. Now we can talk about
Excuse me. Okay, maybe I've misrepresented Feynman. I'm representing myself. I can have an atom. It radiates out. I can reverse all the waves, and it comes right back to the atom. Okay, and the atom is smaller than the wavelength. So it seems to me that we have to give a little bit of credence to that viewpoint, and maybe to suggest that there's more than one way to have perfect lens, or let's just say very tight focusing. And if I could mention two of the ways that have emerged this morning, as far as I can see, is that you could have certain subwavelength metallic structures. Metals are very famous for concentrating electromagnetic energy in their sharp corners. So that's one way. Another way is this way that was suggested by the speaker, who should speak up probably pretty soon. And that is that if you come up with a very fancy distribution of electromagnetic energy, it will actually, in some cases, it will actually concentrate to a very small spot. Have I misrepresented you?
Would you like to add anything, Roberta?
Well, all I have to say that...
Please use the microphone.
Yeah, Feynman was well aware that the second solution of a second-order differential equation existed, but he was also well aware that in the process you violated causality. Is it okay? I don't know if you heard what I said.
Yeah, I heard what you said. I don't agree. I don't see where causality enters in. If I was a really good engineer, then I could bring all those.
Oh, I don't dispute that, Eli. I made a comment to Ulf's work when I said that if you put the source in the position of the image, you can also get the incoming wave. Of course, I agree with that. But that requires that you know what's going on. And in nature, when we try to image something, we don't know what's going on.
Javier, let's have a new voice in the discussion, please. Is there a microphone for Javier?
Can I say something to this? It's already contradicted by experiment, because we offered the field not just one source, but 10 of them, and none of this was active. So we didn't plan where to put some dipole in that could absorb the energy. It was completely unplanned. So you just let the field choose in which hole it should go, and it goes into the right hole. That's it.
Okay. Javier, you had a comment?
I think somehow connected to this the discussion is the fact that all of the light that is emitted from, say, an atom can be absorbed by another atom, provided one makes the right optics that connect the two of them. For instance, if an atom emits like a dipole, and then the other atom is positioned at the, say, the mirror image of a special device, and this has been demonstrated in several papers, in Fish-Drive letters, I believe, by people like Sang-Dodar and others using both classical and quantum approaches. So the relevant question, I think, is that the atom that is absorbing all of the light and is then maximally coupled to another atom that can be far away, at many wavelengths away. The question is, how does that help in terms of spatial resolution? That is, if one moves the receiving atom slightly, is it going to be absorbing the light again, or if the atom that is emitting is moved away, is it going to couple also very efficiently to the other atom? In other words, how does that help for the resolution and to separate the emission for two atoms that are very nearby?
Thank you.
Okay, so may I say something to this? So the issue is you have to what you're saying is true for one atom. So if your detector is just one atom and you move it slightly away, it will still be able to capture the field. And the argument is this: so the diffraction spot is formed, and the atom is sitting there, and if it's still within the vicinity of the diffraction spot, it may capture the energy from it. Now, but the point is, you have to choose at least two atoms, and you're asking which one is going to get the majority of the energy, or even more atoms. That is, I mean, in order to see an image, you have to have several detectors, right? I mean, otherwise it's pointless to talk about imaging. So you have to have like a CCD camera with enough pixels to capture the structure of your original object. And this is what we have demonstrated. So we had an array of those, and then we saw that the right ones got a concentration of energy. And so so the question is not just use one detector, but several.
I'd like to abuse my position as chairman by making a comment here. I do join the parties that disagree with those conclusions, and I disagree very strongly. And I have several reasons why, if I may take the opportunity to say so. First, if you look at the original perfect lens, which does use evanescent waves, that creates an image without the necessity of having any detectors in the imaging plane. It does not need a detector there for the fields in a computer simulation to form the perfect image, whereas Ulf has shown that for his setup, if you do not have detectors there, you do not see super resolution. Now, my second argument is an information theory one, which is that I think we agree that the information in the object is conveyed from the object to the imaging area in the far field. And we also know that an object of a finite size can only radiate so many bits of information, so many angular momenta. And therefore, if you have an object which is very finely structured on a scale that has more information in the object than you can actually radiate, it is impossible to get that information to the object which you need to reconstruct it, unless you have a copy of the object there. And that's the point I think Roberto was making, that you have to have something there to create that near field which is missing from the far field information. And that is true of the Maxwell fisheye, but it's not true of the original perfect lens, because that includes the evanescent waves and creates all the fields you need. So that's my position.
Okay, if I may say something, if I abuse my position as well. So to the first point, I mean, you need to, in order to see this, you need to include a little bit of loss in your material. So if you have a completely lossless negative index material, you don't get that. So you get cloaking instead of perfect imaging. And that's something that was in 2005 demonstrated in a paper one of the first papers on invisibility cloak. So you get resonances that make things invisible if you have a perfect negative index material. If you have a little bit of loss, then that's a different story. And then you can indeed transfer the image for the material. In reality, that's what you have, of course. And the second one is, of course, it's true, you have to put something there. But you don't have to put an exact copy of the original field, but the possibility of creating that exact copy. And that is a photosensitive material that is actually able to capture the original field, and then you get that.
I would put it like this, that if you have, I think one of the confusions is that you're actually putting a source there in the object plane. If we instead put a reflecting object there, and then the source is a beam of light which illuminates that object. So let's take that situation. And then the light scattered from the object forms an image. And if we have no second object there, that image is not subwavelength. But if you put a copy of the object there, that light, which is incident on the object, will scatter from the second object and actually reform into the time reversal of the incident beam. And this is the Feynman point, that that's how you form the time reversal situation. So what you're actually doing is providing a perfect copy of the illumination. You are not providing a perfect copy of the object, and the illumination field is a far field, and therefore the illumination is not structured on a subwavelength scale. Of course, if you have another object there, you do have subwavelength structure, but the subwavelength structure has to come from the second object you place there, not from the fields which are incident. Well, we seem to have reduced everybody to silence between this, so unless there are any more questions. Yes, Sebastian, I could rely on you. Please, your voice is very soft, Sebastian, let's hear you.
So there is one issue which is quite interesting. Well, actually two issues. First, the lens is highly heterogeneous, or at least it's heterogeneous. And second, we rely upon the quality of the cavity itself, the boundary of the lens. So how does the roughness, let's say, of this cavity affects the resolution of the image? For instance, if instead of having a very smooth cavity, it has some roughness.
So presumably this is an issue, and also the inhomogeneity of your material on small scales is limiting the behavior. So it's not the wavelength anymore, but there are other limits coming from it.
Yes.
But I believe, so this is something we don't fully understand, and that needs to be investigated. But I think that those limitations are of a practical nature, not of a fundamental ones, and therefore, in principle, they can also be resolved.
One very last comment, Roberto.
This point is important in the following context. I mean, if I had infinite signal-to-noise resolution, I could also pick up the evanescent modes if I work very, very, very hard. So the point we have to ask is, if I have two sources and I have an image where I have the field before I put a detector, theoretically, if I move a copy of this object around this, I will be able to see it too. But my point is that any noise in there is going to kill you experimentally, much in the same way that the evanescent modes are essentially built into the noise. So my point is, add noise to the problem, and you won't be able to see it too even.
Okay, it's 1:45. It's time for lunch. But before we go, I do have a few administrative points. First, for those who have lunch coupons today, you're asked to please follow the IAS staff and helpers who will bring you to the China Garden restaurant. And you'll need to present the lunch coupon for joining the ASI lunch at the restaurant. If you don't have a lunch program, please refer to the program booklet for locations of other catering outlets on campus. Second announcement, one of our invited speakers, Nikolay Zeludev, has had to postpone his trip for a couple of days. I believe he's ill. But his slot this afternoon will be filled by C.T. Chang. And the afternoon session will start at 2:15 p.m. instead of 2 p.m. Finally, please note that this lecture room will not be locked during the lunch break, so you're strongly advised to take your valuables with you. Thank you.